Welcome back to the afternoon session of our workshop on explainable AI. Our first speaker this afternoon is Rose Yu from University of California at San Diego, where she's a professor at computer science engineering and also affiliated with the Data Science Institute, the Contextual Robotics Institute, the Bioinformatics and System Biology, and Center for Machine Integrated Computing and Security. So without further ado, Rose, it's all yours.
Thank you, George, for the kind introduction. Great. Thanks, George, for the invitation to this wonderful workshop. And it's a great honor to speak here at Caltech, where I spend most of my postdoc. It has been the most enriching experience here. So today I want to talk about some of the recent work from our group. We do spatial-temporal machine learning. We're in UC San Diego. So when we think about explainable AI, the ultimate goal of explainable AI is to increase our trust in AI models and algorithms. However, different user groups have different criteria for deciding whether or not they want to trust the AI algorithms and models. So for common users, when an AI algorithm makes some predictions, they will look at the predictions and ask the question, does it look good? So they will do realization and diagnosis of the outcome. And if they do, they would be able to increase their trust in the AI algorithm. But it comes to scientific applications, which is a primary focus of our group, scientists have studied different definitions. So when we use AI for science, and when the AI algorithm generates some predictions, for a scientist, they often ask the question, does it satisfy conservation laws, which are the first principles in science and engineering? And if the models do satisfy conservation laws, that will significantly increase the scientist's ability to trust the AI algorithms. So there is an intimate relationship between conservation laws and symmetry, which is the focus of this talk, given by Noether's theorem, which says that for every symmetry, there is a conservation law. For example, translation symmetry corresponds to conservation of momentum, time invariant symmetry corresponds with conservation of energy. So by integrating symmetries into deep learning as an inductive bias, we will be able to improve the generalization of our AI models, reduce the sample complexity of learning, and ultimately increase our trust in AI. So let's start with some mathematical notations, just to get a warm up with tools that we use in integrating symmetries in deep learning. And we use group theory. So we know a group is a set with a composition map. And the set has identity. And for every element in the set, there is an inverse element. A familiar type of group is SO2 group, rotation group. So in this case, if we're not rotating an object, this identity, if we rotate it by 60 degrees clockwise, there's an inverse operation, which is to rotate this object counterclockwise by 60 degrees. So equivariance is a type of symmetry. And when we say a function is equivariant or invariant, we basically means when we apply some transformation to the input of this function, it will not change the output of the function. In this case, we say this function is invariant to this group transformation. And equivariance is a more general notion of transformation, which means when we apply some transformation to the input, g of x, it will automatically apply to the output of this function. As an example, let's say we're looking at the velocity field over space, and the function itself is a scaling function, and the group transformation is rotation group. So when we say a function is equivariant, it means if we scale the velocity field by 2, and then rotate the velocity field, it will be the same as we rotate the velocity field by 45 degrees and then scale it. So going through the top right-left route is the same as going through the bottom left route. And if a function satisfies this kind of property, we say this function is G equivariant with respect to a group G. So our goal here is to build equivariant networks, which are it's a class of deep learning models that are symmetry aware. So if we wanted to build a neural network, right, we know a neural network is a functional approximator. In this case, we want this neural network to learn a function that is G equivariant. So the key to build equivariant networks or symmetry aware networks is the composition of equivariant functions is also equivariant, which means if we ensure that between layers, the maps are equivariant, then the entire network is equivariant. By adding residual connections or skip connections to this equivariant network does not affect its equivariance. In practice, we can achieve such symmetry through weight sharing. We are very familiar with the architecture of convolutional neural networks. The reason CNNs are successful in computer vision is its translation invariance. CNNs achieves translation invariance through weight sharing. In this case, we're looking at the symmetry group of shifting. So the two orange blocks here are sharing weights through the same filter, but within the filter, the weights are freely trainable. So in this way, we can design an architecture that is intrinsically invariant to shifting or translation. In a more general case, beyond the translation group, we can design convolutional layers that is G equivariant with respect to any group, as long as the kernel satisfies some conditions, and this condition is called the group invariance under conjugation. So in our papers, we leverage this general theorem and designed various deep learning neural networks that have symmetry built in for different type of groups. As example, we tried to design deep learning models that can speed up turbulence simulation, because turbulence at high resolution usually takes months to simulate, and the goal of this project is to design surrogate deep learning models that can quickly generate the velocity field of the turbulence without going through the numerical integration. However, when we train a neural network to learn the dynamics of turbulence, oftentimes it is only able to forecast of the velocity field for a specific type of dynamical system. And when the distribution of the turbulence changes from training to testing, a lot of the deep learning model would fail. So the goal of this work is to incorporate symmetry as an inductive bias to improve generalization. And this is work done by my PhD student and postdocs. The high-level idea behind including symmetry for improving generalization is that we believe even though the data distribution has changed from training to testing, the laws of physics do not change. And therefore, if we can build neural networks that encode physical laws, then we will be able to enable generalization in a different distribution. So in this case, let's say we're looking at the scaling symmetry. So turbulence have intrinsic scaling symmetry. When we look at a small scale turbulence, when we pour milk into the coffee, and it has some resemblance with a large turbulence when we look at the ocean currents. So the standard convolution shares weights across input by translating a kernel, and hence it's translational invariant. But for scale equivariant kernels, we have to design different ways. So in this case, we must translate and scale the kernel across input to achieve scale symmetry. And that's what we implemented in this paper. Specifically, we wanted to encode scale equivariance in our convolutional layers. And in this case, we're looking at the velocity field of the turbulence. So we can upscale the velocity field up to different sizes, and then allow all these filters at different scale to share weights. And within the filters, the weights are freely trainable, similar to a regular convolutional neural networks. So for turbulence, because it's governed by Navier-Stokes equation, we can also utilize the scaling laws in the Navier-Stokes equation, which is essentially the scaling law of space by lambda and the time by lambda squared. So this scaling operator will directly operate on this convolutional kernel, and then we sum over all the features from different scales, where lambda is a scaling factor. As an example of the results, we can show that this model allows us to build much more generalizable deep learning forecasters. So the experiment is that we take the historical velocity, the past velocity field of the ocean currents, and trying to forecast the future evolution of the ocean currents. But then we're trying to test a generalization case. So the model is trained on a specific scale of the turbulence. But in the testing, we upscale the test data by different factors, and that is showing on the x-axis. So to a regular deep learning model that is not equivariant, because it doesn't know about the changes in distribution, so the forecasting error will explode when the testing data have different scales than the training data set. However, when we use an equivariant, scale equivariant deep learning model, we can see that it automatically learns the transformation from training to testing, and therefore the forecasting error stays robust while we change the scale of the test set. And more importantly, we can maintain the physical consistency of the prediction shown on the right-hand side. And this is the energy spectrum error, which is the energy spectra or energy cascade spectra of the predicted turbulence in the ocean. So we can see again, as we change the test set with different scales, the prediction error in terms of physical consistency does not change. In contrast, the non-equivariant model will have exploding error in this case. Another benefit of incorporating symmetry is sample efficiency. And in this work, we are looking at a much more realistic system of traffic. So traffic is also similar to a dynamical system, a fluid system, except that we also have to model the complex human. So this work was done by my PhD student, grad students, Leo, and postdoc Robin. Our model is built upon the key insight that traffic or many particle systems pertains to intrinsic symmetry. Because we can think of traffic dynamics as a driven many particle system. It's just a more complicated version of fluids in real world. And when we're looking at traffic, there is actually implicit rotation symmetry in our brain, because when we know how to turn right in the North Hemisphere, and when we move to Australia, we still know how to turn right. So in this case, when we want to design an AI model, we also hope our model can make consistent predictions in regardless of the direction that the reference frame sits. So this model should be able to distinguish left from right turns and give consistent outputs. And that's what we designed this model for. So we designed a rotational equivariant neural network model that is symmetric to the continuous rotation group in SO2. We follow the general recipe of designing the kernel to satisfy the condition of group invariance under conjugation. So specifically, we need to design the group representation matrix for SO2, for the continuous group of SO2. So we work with the polar coordinate in this case by looking at the position of different cars or autonomous vehicles. So for every autonomous vehicle, we're looking around at these neighboring vehicles, and we discretize the space according to a polar coordinate. So we allow weight sharing through the orbit, so the weights are shared along the orbits. And then the weights are constrained, or the center is constrained to be a circular matrix, such that the whole thing satisfies a group equivariance under conjugation. And then because we work with polar coordinate, that the kernel or the cross product angle space, the SO2 cross SO2, it becomes a torus. So we call this kernel a torus kernel. So in this case, we wanted to use this type of neural network to forecast the future positions of vehicles. So given the trajectory of multiple vehicles, we're going to encode the past position and the velocity of multiple cars simultaneously with our design neural network. And then we map the historical data into some hidden representations using our continuous convolutional kernel. And then we will use another set of continuous convolutional neural network to detail the future or predict the future velocity of multiple cars at the same time using the hidden representation. So for both the encoder and the decoder part, we have our own proposed continuous convolution. And in this case, we're predicting the delta x, which is a difference in position for multiple cars at the same time. So when we look at the prediction performance of our model, we can see that compared with the non-equivariant counterpart, which is a continuous convolution, by simply adding equivariance or symmetry to this model, we were able to achieve much more accurate forecasting error in terms of average distance error. And we can also reduce the number of parameters in the model by 95%. So this is extremely important when we want to deploy this kind of model in embedded systems in cars, where the size of the model matters. Another interesting finding is that by encoding this kind of inductive bias into the model, we can show that the equivariant models can achieve similar prediction performance with much fewer number of data points. So we are able to reduce the number of examples we need to train the model by 80%. And you can see that the validation loss dropped really quickly within 3,000 examples. Finally, I want to talk about some new work that I'm very excited about, because in the previous two works that we have showed, incorporating symmetry allows us to generalize to systems within a certain group transformation. But in real world, but still these works are focusing on specific dynamical system with the same initial condition, boundary condition, and parameters. And this new work that we did is trying to design models that can generalize beyond the same system. And then we can have a model that can predict for systems with heterogeneous parameters, external forces, and boundary conditions. And again, we want to forecast the turbulence, right? But we want to focus on turbulence with very different dynamics. And it's work done by my PhD student, Ray, and postdoc. Okay, so let's consider two fluid flows with very different degrees of turbulence. So in the top row, we can see that the flow is relatively steady. And we wanted to forecast the future evolution of this flow. But then we want to test a much more challenging case where the model has never seen the flow in the bottom, right? And we want the model to be able to predict this type of flow with much more turbulent forces. So the ultimate goal of meta-learning is to develop a model that can generalize to flows with different buoyant factors, forces. And the key idea behind this work is that we observe that even though the flows are governed by the same equation, the difference of buoyancy forces usually would require separate models. But if we can explore the symmetry in the system, then we wouldn't need separate models to forecast this type of dynamics. We only need a unified one model to forecast the dynamics. So the key idea is that we can explore the symmetry and find models that can exploit the shared time invariant hidden features in these dynamical systems. Because these two flows, even though they have very different behavior, they actually share certain time invariant hidden features, which can be encoded in the design of the deep neural networks. So we proposed a meta-learning framework to enable models to generalize to very different dynamics. And this model is called DIAD, or Dynamic Adaptation Network. We used a latent variable modeling framework by identifying each forecasting task with some parameters. So in this case, the parameters are different external forces. And we define a forecast task as forecasting for a specific system with a particular type of forces. So we learn multiple tasks simultaneously, where we generate different data with different external forces and train a model simultaneously using multitask training. And our model consists two parts, so an encoder and a forecaster. So this encoder is specifically designed to disentangle the time invariant hidden features. So it uses a time shift invariant architecture design. In addition, it uses weak supervision to enforce the latent representation Z to be time invariant. So this loss function for the encoder consists three parts. The first part is the task parameter. So we give some weak supervision to the model, indicating the buoyancy factor. So an example of that weak supervision can be the average velocity of the turbulence flow. So the second part is the hidden feature inferred by the model for this specific task. And we want these latent features to be time invariant. So therefore, we constrain them to be not changing across timestamps. And to avoid the pathological cases of Z to be too small, we also add a regularizer to encourage the latent space to be more interesting. So once we use the encoder to learn this latent space or time invariant latent space, we can feed this latent hidden features to adapt the forecaster network. So this is similar to the style transfer literature in deep learning, where we use adaptive instant normalization and adaptive padding to adapt each of the layers in the forecaster network according to the learned hidden features. And in this case, we will be able to predict turbulence with completely different buoyancy factors or any type of parameters we want. So we can look at the performance of our model versus a lot of the state-of-the-art meta-learning methods, such as MetaNet or MAMO. We actually evaluate on two types of meta-learning scenarios. The first meta-learning scenario is to evaluate the model's ability to extrapolate into future with different initial conditions. The second scenario is to look at the ability of the model to generalize across different tasks or dynamical systems with different parameters, such as external forces. So we evaluated on three different turbulence, turbulent flow, sea temperature data, and ocean currents. We can see that across all scenarios, our model is able to achieve competitive performance and make the most accurate predictions. So for the ocean currents, we also measured both the prediction accuracy in terms of RMSE, as well as the physical consistency in terms of energy spectrum error on ocean currents. Let me show you some of the predictions from our model where it has never seen before, right? In this case, we train our model on a set of turbulence with different buoyancy factors. And then during inference, we will give model completely different turbulence and ask the model to do forecasting. So the top row shows the turbulence with buoyancy factor 9, external force at 9, right? And when we play the video, which is the actual forecast from our model, we can see that our model dyad is able to capture very small scale dynamics in its turbulence, quite close to the target turbulence that we want. Whereas the baseline model, such as the modular-based meta-learning framework or the regular multitask learning framework based on ResNet, it cannot learn the small scale dynamics in this type of turbulence. We can also manipulate the latent space that we learn, the hidden features, and ask the model to predict a much more turbulent phenomenon. So in this case, we manipulate the latent space and ask the model to forecast the turbulence at buoyancy factor 21. So the turbulence becomes much more vibrant, but still our model can capture the accurate behavior in this turbulence. Okay, to conclude, I would like to argue that if we wanted to enable explainable AI in science, we really need to pay attention to the conservation laws that we know from first principles. So one way to do that is to incorporate symmetries into deep learning for learning complex spatial temporal dynamics. So talk about 3 works from our group: the Equivariant Network, which is to incorporate symmetry designing equivariant networks for differential equations. And ECCO is a type of equivariant networks for forecasting multi-agent trajectories with rotation symmetry. Dyad is a way to incorporate symmetry in the hidden features rather than the data space. It allows us to control the latent space and predict in a completely different heterogeneous domains. And I would like to, you can also check out the code and the data as the papers on the website and follow me on Twitter. And I would like to thank the funding agencies for supporting this work.
Thank you, Rose.
Thank you.
We have a question from Christopher E. What prevents the hidden features Z from being a constant non-zero vector?
Because we actually, the difference in the training data will present it to be a constant non-zero.